Okay, now we've got some space back here that we can work with. And so let's do another example in which we have the intersection of a bunch of convex sets, which will therefore be a convex set. And this is going to be different in a couple of respects. One, it's going to be in R2 instead of in R1. And second, the example is going to be kind of related to economics, kind of related to consumer theory. And so let's do the following. Let's put a diagram down here, and let me use a different color here for the axes. X1, X2, and let's suppose that this is a kind of a commodity space. So you've got two commodities, two goods, and let's take one point in the one bundle, if you like, in the commodity space, and let's let that be this bundle right here, and I'm going to just give that a name, X circle, and that is X1, X2. And what I want to look at here is I want to look at all the budget constraints that go through that bundle, that include that bundle on the budget constraint. And so if I'm going to do that, then I have got a budget constraint that looks like this, and I'll call it B for budget constraint. Get that off of there. And I'm going to say B sub P because the budget constraint is going to be the set of all bundles or points in R2 plus, because we don't think the consumer is going to be able to consume negative amounts of anything. And so this is such that P dot X equals P dot X circle. Or put that another way, P1X1 plus P2X2 is equal to P1X1 circle plus P2X2 circle. So for each price vector or price list in R2, we get a budget constraint, a line going through the space here. And so let's just take a couple of examples. Here's an example where I have actually P2 is 0 and P1 is positive. And so that's the budget constraint in that case. In fact, I've even put on this. This is where P2 is 0 and P1 is positive. And then I've got other budget constraints that look like this or like this. I'm just looking at budget constraints that go through that point. And so let's also note that there's a budget constraint that is horizontal that goes through that point, in which the price of the first good is 0 and not the second good. So I've got all these budget constraints. I've got one budget constraint for every price list in R2 plus. I'm only looking at positive or 0 prices, no negative prices here. So the budget constraints are all downward sloping or possibly vertical or parallel. And so I want to look at the intersection of all of the of these budget constraints. Well, that one's easy. Clearly, the intersection of all the budget constraints is just the singleton consisting of this bundle here. That's nothing, that's pretty uninteresting. But now, let's look at the intersection of all of the budget sets. So what I'm going to do now is I'm going to redefine B to not be the budget constraint, but the budget set, which is everything on or below the budget constraint for every possible budget constraint for different P's. So it's everything to the left of this or everything below here, depending on the price list. Okay, so let's even just sort of do a couple things like this to just indicate that it would be everything to the left, let's say, of the vertical budget constraint. So now what I've got is, for every price list, I've got a set, and the set is a convex set. It's the set of all things above the axes or on the axes in the positive, non-negative quadrant, and below the budget constraint. In every case, a convex set a triangular region, except in these two cases here where it's a long strip. In every case, a convex set. So these things are all convex. Therefore, if I take the intersection over all price lists in R2 plus of B sub P, that has to be convex too. Well, what is the intersection of all these things? Clearly, that's this little rectangular region that I'll call S down here. That's the intersection of all of these. It's this rectangular region, which is convex. Now, notice that in this particular example, I could have generated this little rectangular region by just looking at the intersection of two of the budget sets. All the budget set to the left of the vertical line for that price, these price lists, and the budget set below this line for all the price lists with P1 equals 0. So just two price lists would have generated this rectangular set. I wouldn't have had to take an infinite intersection. But now, let's suppose that I'm only going to consider price lists that have no 0 prices. Both prices have to be strictly positive. So now I'm looking at price lists in R2++. That is, all the price lists where both P1 and P2 are positive. So now the vertical line and the horizontal line, the budget sets defined by those two budget constraints are no longer in this collection of budget sets. And so the question is, what do I get? Well, you can easily check and easily see that the intersection here is still the same set, but the only way I'm going to get that set by intersecting some of these budget sets is to intersect an infinite collection of the budget sets, as I'm doing here. I'm intersecting clearly very much an infinite collection of budget sets, and the intersection of all those sets is still just this closed set, this rectangle, including its boundary, capital S, which is a convex set. So this is just an example where we've moved from R1 to R2, and an example which has some economic consumer theory type content. And we actually will see situations like this in the microeconomics course. So we've now kind of looked at the notion of intersection of convex sets. Now, if we have any arbitrary set S, convex or not, and we take the intersection of all the convex sets that contain that set, we call it the convex hull. So let's see what the convex hull is going to look like for some of these sets. This is not interesting. We could take that off, but we'll take that off in a little while when we take this other stuff off too. But right now, let's just look at these sets up here and look at the convex hull of these sets. So what would be the convex hull? Now here, let me again use S as, let's let S now be S1 union S2, not the intersection. So S is now this funny shaped region that is circular up here, but at the bottom of a triangle down here. It's everything inside, in fact, let's even say, it's everything inside the boundary of this. And down here. But I want to look at the convex hull. So what I'm going to do is I'm going to say, I'm going to look and see how this works. I'm going to look for a convex set. In fact, if I can find it, the smallest convex set that contains S as a subset, right? So I'm going to say, let's look at this set here. So now it's the set whose boundary is this sort of bluish grayish line here, okay? That is, clearly it's a convex set. and it is a set that contains S, and I will maintain that that is the convex hull of the set S. It is the intersection of all convex sets that contain S. And let me make a little argument to say why that's true here. Okay, so first of all, I'm looking for the intersection of all the convex sets that contain S. So if this set is a convex set and it contains S, as I'm maintaining it does, it seems obvious intuitively, this is a convex set and it contains S, then the intersection of all convex sets containing S has to include this, because that is one of the sets in that intersection. Moreover, any larger set that is a convex set containing S, when I intersect it with this, all the rest of the stuff is irrelevant. So any larger set I don't even have to consider. I only need to consider this set here and then see if there's any smaller sets. Okay? But of course, I can see that any subset of this set here, at least intuitively I can see, that if I throw out any of these points, then there's going to be a that point is going to be a convex combination of some points in S. So for example, let's just suppose I throw out this point here. So I'm considering this set here, but not that point. Well, that point is that point, the set that I end up with that point here, that's not a convex set anymore, right? So if I delete that point, it's not a convex set because, in fact, it's not a convex set because I can just take 2 points in here. You only have to be in S. And that convex combination is not in there, so that's not convex. So that little kind of informal intuitive argument tells me that the convex hull of this non-convex set S is the set here, and it is the intersection of all the convex sets that contain S. Well, you can see that it's basically the smallest convex set containing S, and that really is what we mean when we say the intersection of all convex sets that contain S. And so let's see what that does over here. Again, over here, S is not convex. So if I want to look at all of the convex sets that include S, well, one of those convex sets is going to be the set consisting of this boundary plus the original boundary over here. And so everything down here is going to be everything in here, here, and down here. That's going to be in the convex hull of this non-convex set S. And again, you can see that intuitively this is the smallest convex set that includes S as a subset. And again, you can make the same argument as over here. This is a convex set. It contains S. So the intersection of all convex sets containing S has to, that's one of the sets in the intersection. So that's going to be in there. And could there be a smaller set? Again, if I throw out any of these points, the resulting set won't be convex. So it does appear that this is the convex hull of this funny non-convex set over here. And so it turns out that there is a characterization of the convex hull that is useful, and that involves the notion of convex combinations of vectors, but convex combinations of more than 2 vectors. So you'll recall that in the definition of a set being convex, we said it's got to be the case that 1 minus lambda times x plus lambda times y has to be in the set. And we said that's a convex combination of x and y. There's a coefficient here and a coefficient here. Notice that I could just as well have written this as follows. I could have written alpha 1 times x plus alpha 2 times y. where alpha 1 is this, alpha 2 is this, and then note that alpha 1 and alpha 2 are certainly both greater than or equal to 0, because lambda is, in our definition, lambda is actually bigger than 0. So alpha 2 is bigger than 0, and lambda is less than 1, so alpha 1 is bigger than 0. And what we're going to do here is include the 0 coefficients, because if alpha 2 is 0, I'm at x. And in the definition of a convex set, the x that we start with is in the set. Same thing, if alpha 1 is 0, we're talking about alpha 2 times y. And I left out one more thing here, and that is that alpha 1 plus alpha 2 have to add up to 1. So all of the convex combinations of x and y here could be written this way instead of this way, and we would say the convex combinations of x and y are all of the sums of scalar multiples of x and y, where the coefficients, the scalars, are both non-negative and the scalars add up to 1. So now it's starting to really be reminiscent of when we talked about linear combinations. Clearly, this means that this, which is the same as this, is a linear combination of the x and y vectors, but it's just a restricted linear combination where the coefficients have to satisfy these conditions here. And as soon as we recognize that, we recall that we didn't talk about linear combinations as just linear combinations of two vectors. We talked about linear combinations of any finite number of vectors, and that's what we have here. We say that a vector is a convex combination of a finite number of vectors, here v1 out to vm. It's a convex combination if it's a linear combination, but a linear combination where the coefficients all are non-negative and where the coefficients add up to 1. So what I'm going to do now is I'm going to take off, well, in fact, I won't do that. Let's keep these things on here for a moment. Let's take this off of here to get a little room. Let's see if I can get that off of there. Okay. So let's look at a situation where m is 3. So I have 3 points. So let's take this point, and this point. Call those v1, v2, and v3 in R2. And I want to look at the convex combinations of these 3 points, not just the 2 points. Well, of course, one of the convex combinations is where the alpha on 3, alpha 3 is 0, and I've just got a convex combinations of v1 and v2. So those are clearly, all of these are convex combinations of the 3 vectors. And in fact, let's just write that down here. We're looking at convex combinations of the 3 vectors v1, v2, and v3. All of these are convex combinations where alpha 3 is 0. These are the convex combinations where alpha 1 is 0. And these are the convex combinations where alpha 2 is 0. But then we have all these points in here which I can generate by taking convex combinations of v1 and v2, and then taking a convex combination of those with v3, which I can show easily is then a convex combination like this. That is a linear combination where the coefficients do add to 1. In this case, alpha 1, 2, and 3 add up to 1. So all the things in here are convex combinations of these 3 points too. So the set of convex combinations of these 3 points is this triangular set here. Suppose I have a 4th point. Let's take one over here. Well, now all the convex combinations of these 4 points is going to be everything in here. Suppose I have a 5th point. Suppose that 5th point is inside here. I can take the convex combination of all 5 points, but of course that 5th one is going to be not really relevant. I can have an alpha times that, but if I do or I don't, it won't make any difference. The set's still going to be this. So the set of all convex combinations of a set of points is starting to look a little bit like what we did here with this convex hull. Clearly, the convex combinations of those first 3 points was the convex hull of the set consisting of V1, V2, and V3. Right, so that would be the convex hull of this set here, those 3 points. And if I added a 4th point to S and then took the convex hull of the 4 points, I'm going to get this. So it's really looking like the set of all convex combinations is related to the convex hull. Well, let's see what we have here. First, we have a theorem that says a set's convex if and only if every convex combination of vectors in S is also in S. And that's a theorem that you're going to prove as an exercise. It's a really good exercise, but let me say a little bit about how that proof is going to go, give you some idea. First, it says if and only if. So we have to prove it both ways. So let's notice that if every convex combination of points in S, and let's take the triangular region here. Let's suppose that's S. Okay? So let's suppose this triangular region here is S. And now that's convex. And so it has to be, this says if every convex combination of vectors in S is also in S, then S is convex. That part's easy to prove. In fact, that's straight from the definition, because if every convex combination of vectors in S, like these, and then a convex combination, if every convex combination is in here, then certainly the convex combinations of just pairs of vectors in S are in here. So clearly, if all convex combinations of vectors in S are in S, then all 2-point convex combinations are in here, so S is convex. So the proof in that direction you basically don't even have to do. I mean, that is straight from the definition. So the only part that really requires any real proving is to show that if I have a convex set, then it must be the case that every convex combination of vectors, no matter how many finite vectors I have that I take the convex combination of, we have to show that's in S. So that would mean that I could take maybe half a dozen vectors in this triangular region and take the convex combination of those vectors. That would have to be in S as well. That's what the theorem says when we're going in the direction that we say a convex set will contain every convex combination of vectors in S. And you can sort of see from what we did up here that that must be true, because if I take a bunch of vectors in S, then I take the convex combination of all those vectors, I get something like we did up here. That intuitively, that's clearly still got to be in S. So how would we go about actually proving this theorem in this direction? That if I have a convex set, every convex combination of finite sets of vectors, that's going to be in S. That proof is a proof that you absolutely should do by induction. So it's a really great exercise for an induction proof, which is where the proof is not as obvious as it was back when we talked about proofs by induction. The examples we gave there were really straightforward and almost obvious how to do them. This one's not that obvious, but it's still pretty straightforward. So you should do a proof that if a set is convex, then every convex combination of vectors in S is going to be in S, and you should do that by induction. So let's see here. Now this theorem says what we just kind of guessed a few minutes ago, and that is this close relationship between convex combinations of vectors and the convex hull of a set. This says the convex hull of the set is actually just precisely the set of all convex combinations of vectors in S. So that means, remember, the term characterization or characterization theorem. This is clearly a characterization theorem that characterizes the convex hull of a set as the set of all convex combinations of vectors in the set S. So the set S is generally not convex. Convex hull will be convex set, and it will be the set of all convex combinations of vectors in S. Just what we kind of guessed up here when we were talking about convex combinations. In fact, you'll notice that the first of the two theorems, the theorem above here, that is really technically also a characterization theorem, because it says a set's convex if and only if every convex combination of vectors in S is in there. It's not one that we typically refer to as a characterization theorem, but it is. The second one, this theorem here, that is very much something that we use as a characterization of the convex hull of a set. So let's take some things off here, and then we'll move on to some concave and convex functions.